Guys, this is Nikhil and you are learning golang with me. In this particular session, I'll be explaining what is the potential defect or what is the defect in the Zookeeper golang library and how the network partitioning plays a key role in that particular edge case. This is the edge case that I have encountered with in my platform, and that's why I decided to get into the implementation, and that's how I encountered and identified the problem and then solved the same. So I already set up the background, the context has already been established. Just to repeat, to reiterate the same thing, you have the set of Zookeeper clients. Because of leader election, because of some kind of situation in which the distributed lock is required, you go to the Zookeeper and then you request for the lock. In normal circumstances, Zookeeper allows only one client to proceed with the lock because lock cannot be held by the multiple clients. It's not the counting semaphore, it's the binary semaphore. But in special edge case in which the network partitioning plays a huge role, the Zookeeper actually allows client to create a lock, but there is no trace of the lock because the Zookeeper packet, which is the response packet about the lock handle, is lost in between, and client is unaware that the lock has been created. For client, it is the ZK connection close issue or ZK exception, and then client tries to recreate the lock, but from Zookeeper side lock is already there, and then the Zookeeper just simply adds the new lock request into the priority queue, and there is a deadlock. So just imagine that server 1 has successfully got connected to Zookeeper, tries to acquire a lock, and then there is some kind of network partitioning. The lock is requested with sequence number 000. Server 2, server 3 and server 4, they are the lazy ones. They go to Zookeeper in some after some time gap, and that's why they get the 001, 002, 003 as a sequence number. Now, if there is any partitioning issue, network partitioning issue in between server 1 and ZK cluster, when ZK cluster actually sends the response to the server 1 about the fact that server 1 has successfully got the lock, and also the response contains the lock handler. If there is any issue, then server 1 says that hey, Zookeeper connection has been closed. It waits for session, the Zookeeper cluster waits for the session timeout expiry. If the session timeout is higher than the reconnection time, then Zookeeper cluster remains, or it keeps the lock. The lock is there in the Zookeeper cluster. The Z node created by server 1 is there, but server 1 is oblivious of that particular fact. And this is the same issue that we are going to demonstrate in this video, and this actually leads to a deadlock because no server gets the lock. Zookeeper says that lock is acquired by one of the client, so either it has to be released or there has to be session timeout. For that you have to close the connection, or you just stay in the same situation. And in golang, the library waits on the receiver channel, and that's why it's a deadlock, complete deadlock. So I will just simply go and do TLS on my path, which is root test, and this is my Zookeeper client tool. And now I will just start my debug session in which I will request for a lock, then I will let the library create the sequence number, and I have to be very fast so that Zookeeper actually does not come to know that there is some kind of network issue. Now over here I will simply create or some failure, and you can now see that the lock exists. I will simply go ahead and scan for the Z nodes. This will get the ZK connection close issue, once it is done, I will simply restore the connection, and now over here you will see that you have the error which is ZK connection issue, connection closed. I will proceed now. Because of the error, there is no passing of the sequence and there is no lock. So this particular lock object does not have the lock path. Now I will simply proceed. I will try to reacquire the lock. I will go back. Over here you will see that lock still exists. For Zookeeper, client 1 is there, lock exists, and now again client 1 is trying to request for a lock, and then over here lock path is null, is nil, or is empty. That's why it will proceed. It will create a new path, and now this time sequence number is 003, and then now over here it will parse it. You will find sequence 3, you will find children, number of Z nodes are 2 under this path, which is root test, and now this particular logic gets executed. Just remember that initially when there was ZK connection close exception, this logic was simply, it was kept because of this particular return of the error. Now over here you will see that our current path is 3, previous path is 2, and on Zookeeper now you have got 2 items in the priority queue fighting for the same lock. Or for Zookeeper, 002 already has a lock, 003 is fighting for the lock. Now this particular library says, hey, there is already a lock acquired by some client. It is oblivious of the fact that this is the same client that has acquired a lock in the initial run, and there was some kind of network partitioning issue, and now you will see that it goes into infinite loop. Now this is the loop, the break condition that actually is responsible to actually confirm and acknowledge that the lock has been acquired, but now it does not get satisfied, it just gets into the infinite loop. And now, my friends, over here, this particular library is infinitely. So now over here you see that I will have 003 and 002 waiting for the same lock, and there is no any progression as such. This is the deadlock, or it is a situation which is known as the deadlock. And this is the edge case in which you have the network partitioning, you have the failure in that. For the Zookeeper, the client is still there because of the session timeout expiry has not happened, so it will not kick the Z node, right? The Z node, this particular one, which was the first request for the lock that client 1 has requested for, and now you will see that it's in the deadlock. Now what I can do is I can simply copy this and clone this project to mimic the client 2, and there will be one more request. So if I just copy this, I should not be doing all of this, but just for simplicity I just want to do so. So let me just clone the project. So let me open it in the new window. Meanwhile, let's go back and check. Okay, lock is still there. My first app client is still waiting for the lock to be released, and it's not going to happen unless, as I said, either you have the real connection issue or somehow the server one goes down. So now you can see that this is waiting for my lock, so connected to the terminal and still it is ready, right? Now let's go to my server 2, which is the clone, and believe that I already imported the one. Is not copied. Then we got it. And then now I will again do the same thing. I will say I want to obtain the lock on the same path, and this is actually mimicking my client 2, and you can see that it is connected to the Zookeeper. If I go to the Zookeeper, you should see 3. We have 02, 03, 04. If I just simply again clone 2 to represent my server 3, and if I open it, this one I will also create another one just to create my server, this 4th server. And again over here, what I just want to showcase you what really happens when it becomes a deadlock. Now you can see that 03, 02, 05, 04, and now we have one more, which is which is your clone 3, which is actually our server 4, and then you have the same thing. So now this time around, let me just take the privilege and showcase you what's there, right? So what happens? So we will come over here, and then it will again get to this point, and then it will get stuck, right? So go back. Now that the new path is created, this is 006, and you have again all of the scanning of the Z nodes. This time around you have 5. Remember, we only have 4 servers, so if I just go back to my deployment, then you only have 4. So ideally there should be only 4 at any point of time, right? That should be the max. But because of this particular edge case, you have n plus 1, that kind of number. Again, it says, okay, sorry, you are the one that is not having the lowest sequence number, so you will have to wait, and then it goes into all of these iterations, and finally it reaches over here, and then now you will see that you have one more 03, 02, 05, 06, which is the latest one, and 04. I can continue playing with this. This will get stuck. As I said, hours and hours I've seen that there is no progress and it's a deadlock. Now, obvious question is what is the solution, right? That's the obvious question. The solution is this pattern actually specifies that whenever the first server, so before coming to the solution, let's understand the pattern, right? This will help us to find out the solution. Then the issue is, when the first requester gets into the Z cluster, creates the lock request, lock gets created, but still, because of the fact that there is some kind of network partitioning, and after the network partitioning, server 1 is able to reconnect to the Z cluster, which is part of the library itself, and this is the specification that is being governed by the Zookeeper itself. Because of that, the server 1 actually creates a lock, but it is under impression that the lock has not been created, correct? So we have to fix issue in such a way that server 1, when it actually reconnects and again tries to create the lock, it has the track of the old path, the new path, or the lock path that it created to acquire the lock, and then it should check whether the lock exists. So this is the code that I have added, and what it does is the same thing, which is this part, in which this part was added so that in case of the connection closed, you have the recheck. So actually there was one issue, and then because if there is a rest condition in the server crashes, after it clears zones. This is the same situation, right? Currently we are facing the same situation, only the place is different, or the sequence of event is different. The event at which, or the point of time at which the network partitioning happens is simply the different. So I am actually using the same logic to solve the problem, and then I am just mapping, or I am just keeping the trace of the old log path that I have created, the sequence number that I have created for the same client in the initial request for the same path. So this should be initial previous request for a particular path for a particular client, and that's how it should be. And then if the lock exists, then simply it knows that it is the one that has acquired the lock, so it can proceed without going through all of this, because this is not really required. For Zookeeper side, the lock exists. You can simply find the lock by just scanning through the Z nodes, and then just proceed with your job and routine as it is, the normal routine, right? The happy scenario. Now over here you should handle the error, because while checking the log, it may happen that the ZK connectivity again goes for a toss, and then you get the error. So this will return as false, and then it may proceed, right? It will proceed. So over here you should handle the error, and then only if this lock exists is false, there is no error, then only you proceed to the actual lock request. Otherwise you are sure that the lock already exists and you are the one who holds the lock. So that's it. I'm gonna now create the issue in the Samuel repo. I will create the pull request, and I just hope that this will get approved and it will be fixed in the upcoming release. That's it for now.